In the time frame of 15 or 20 years ago, Alan Kay conceived of the Dynabook, which most of you probably know is a conceptual forerunner of the PCs and probably some future machines that we've not even seen commercially yet. Alan Kay obviously is a man who's always been ahead of his time. He was the inventor of the first Smalltalk. Some of you may know that there were actually several Smalltalks. The one that you now know as Smalltalk 80 was the fourth or fifth in a sequence of Smalltalks. Alan Kay did that very first Smalltalk. And currently, he is an Apple Fellow. And prior to that, he was a chief scientist at Atari. With credentials like that, I found it interesting to note in his biography that the only professional society of which he is a member is the International Society of Organ Builders. Without taking any more of Alan's time, let me now bring up Alan Kay.
So I have the fees. Oops. So I found it necessary when giving talks on the East Coast to put this slide up so that people who might be offended can leave early. I thought this might be an especially appropriate place. Well, I think a good way to start off is to recall a statement by William James made about a century ago about the three stages in the life cycle of any idea. And the first stage is that the new idea is condemned as being the work of madmen. And then a few years later, it's remarked on as being commonplace and obvious all the time. And the final stage is when the original condemners claim to have invented it. I think we're at that stage now with objects and window-oriented and pointing user interfaces, which to me means that they must be hopelessly obsolete. So we're actually having a symposium here about a patient who's already dead. But in the grand tradition of computer science, will live on for at least a century. This is going to be a different talk than Norm's talk. Norm's talk is a practical talk by a person who got interested in object-oriented programming as a way of implementing large-scale, complex systems in the context of a university, where you don't have a lot of people to do the work, and a lot of the work is transient. And this need to deal with complexity in a way is one of the main selling points in object-oriented systems. And people have this notion that because object-oriented systems are usually worked on by small groups, that it's something mainly for small groups. And the main reason small groups use it, I think, is because it's one of the few vehicles that a small group can do truly interesting things in a short time. But if object-oriented systems are implemented in a thoughtful way, then by their very nature, and we'll talk about this in a bit, if the protection mechanisms that are inherent in the notion of object-oriented programming are also implemented, which they often aren't, then one should be able to organize very large-scale projects as well. Because the whole joy in the object-oriented design is the notion that when you put an object in the system, it should be able to make use of what's there, but its presence in the system shouldn't disturb any other object that's in the system. It should be something that is self-contained. It should not be able to be destroyed by the system, and so forth. And so in an object-oriented system that's well designed, you should be able to add new knowledge in an incremental fashion, almost linear fashion. Now, a little bit later, we'll talk about a couple of the places where that isn't really true and maybe some of the solutions for it. But I thought a good way of starting off would be to just take a look at a couple of object-oriented systems of the past, or almost object-oriented systems. And the first one, and I understand there were only a few people here last night to look at it, so I have an excerpt, maybe this is even a different film, of Ivan Sutherland's Sketchpad, which was one of the earliest object-oriented systems, although Ivan didn't really quite think of it that way. There's an interesting history behind it. So let's show that first tape. So this is implemented on a computer the size of this room. TX2, the last computer in the U.S. to have its own roof. This is what you saw there was the very first implementation of the rubber band technique. And here's something you don't often see, even in graphic systems today. He did a rough sketch. He pointed to those edges and told them he wanted them all mutually perpendicular, and Sketchpad figured out how to do it. We just saw that Sketchpad was also the first system to have a window. This is all done in 1962. There he pointed to those two lines and told them that he wanted them to be parallel. And now the constraint is to be collinear. So these little dashes will be precisely lined up over the lines underneath. This is the first time when people discovered that the light pen was not a good input device. And in spite of that, it's been reinvented at least 90 times in the last 25 years. So he's made a hole in the flange, and now he wants a rivet. And again, the whole idea behind Sketchpad is you should be able to quickly sketch in an approximation of what you wanted. He's going to use that as the center for the arc, and then get the system to complete the drawing by implementing various constraints or rules. And here he's saying make those four lines mutually perpendicular. The doing of that pulls the diagonal line, which pulls the center, which pulls the arc, which makes a perfect rivet. So this is also the first non-procedural programming system. So showing that no matter what you do, and of course he could have added further constraints that would constrain the ratios of those sides, so that no matter how you distorted it, it always would come back to something that was the same relative size. So that was a master, what we call a class today, and here's an instance of that rivet. The instances can be scaled and rotated in real time. Now you might wonder, why is the display jumping around like that? Well, I didn't have displays back then. The TX2 here is putting up every screen individually. In fact, memory for each separate dot. So this is a software-oriented display, and when you put up a lot of dots, it starts flashing because it's tracking the pen. Here are a couple more instances. This, you might imagine, led to the development of better displays. Now, he doesn't like the cross piece on the rivet, so he goes back to the master and says, make those invisible. They're still there, but they're invisible now, and lo and behold, we see that the instances feel that change dynamically. And remarkably, Sketchpad even had a form of inheritance. It was actually one of the first object-oriented software systems. So now he's made this constructed thing into a master, and now we can get instances of it. I once asked Ivan Sutherland many years ago, how is it possible for you to, in a single year of 1962, to do the first computer graphics system, the first non-procedural programming system, and the first object-oriented software system? And he said, well, I didn't know it was hard. Okay, stop the... Made a tremendous impression. I had to learn it, I guess, 22 years ago now when I first went to graduate school. Before a desk at the University of Utah, Dave Evans had one of these theses he would hand out, and you had to prove that you understood it before you were allowed to sit down. And I think I might... This isn't worthwhile looking at in any detail. Maybe I'll just use this from now on so I can move around. The main line here, this is essentially the pathway that I took getting interested in this stuff. I was in the Air Force, and there was a file system on the Burroughs 220 that was what we would call today object-oriented. Back in those days, they didn't have operating systems. Of course, and these days, they don't have operating systems either. Back then, there was more excuse for it. And the Air Force had the problem of how can I hand data tapes around Air Training Command. They all had Burroughs 220s, but there was no standard operating system. And so somebody, some genius in the late 50s, came up with the following idea. He said, well, what if we had a tape format like this? Each long tape record is going to be made up of 3 parts. And the first part is going to be a relative transfer vector into the second part, which is going to be a bunch of Burroughs 220 code. That 220 code will know how to interpret the third part, which are going to be our unit records. So all you have to do when you get one of these tapes is you simply read the transfer vector, the front part of it, into a special place in core, and then you can do anything you want with these tapes because we'll have a standard protocol in this transfer vector. That's the way that file system worked back then. Heck of a good idea. I was just mentioning to somebody this morning that the first time I ever did what we would call object-oriented programming today was done on the 1401 in autocoder because we used this technique on the 1401s there as well and made up macros to allow us this generic access to things. Terrific idea. Why didn't it last? Well, COBOL actually drove it out. The adoption of COBOL as a way of getting ahead actually gave us a weaker metaphor that we're still saddled with today. The Burroughs B5000 actually implemented these ideas in hardware. It antedates Sketchpad, and probably 7 out of the top 10 ideas ever thought up in software are actually implemented in the hardware of this machine. Burroughs made the enormous mistake of trying to explain this machine to their customers back then. They actually hired college graduates and taught them how the machine worked so they could go out and tell the customers how good it really was. And that was, I think that was the third machine that I learned back then, and these college graduates scared the heck out of all of these old data processing managers who were just struggling out of punch cards, and the machine was late as well, so it just never caught on. Sketchpad, and then Simula was the first programming language that I would call trying to be an object-oriented language. And there were 2 versions of it. In between, I designed a language called Flex, which is an attempt to simplify Simula. And in some sense, some real sense, the Smalltalks were an attempt to simplify Simula as well. But there are all these other things that fed into it over here, of which the most important ones for, I think, object-oriented programming are the Lisp influences, and over on this side, influences that are basically either philosophical or coming out of cell biology. Now, the reason I bring these up is because I think it's critical when thinking about object-oriented programming not to look at the systems that are out there today and think this is object-oriented programming, because in my opinion it isn't. To me, Smalltalk 80 is not an object-oriented language because it lacks one of the things that I thought was most important in object-oriented design, and that is differential protection, which means that you should be, when an object is put out into the world, it should be able to protect itself against various senders. So for instance, if you have a file object, what you would like the file object to be able to do is to discriminate about who's sending it the message to change byte number 8 in the file. And it's possible to do that in Smalltalk, but it's not set up to actually do that. You can in Smalltalk, you have to instrument every method that you want to protect in order for it to do something. In the earliest Smalltalk, it was combined with what's known as capability protection. Objects were seen as a generalization of capability protection, and that protection was built in so that no object could command another one. And to me, the biggest difference between whether you really have an object-oriented system or not is whether you are really sending messages or not. In Smalltalk and Objective-C and C++ and all this, you aren't really sending messages, you're actually just doing subroutine calls, which means that in some sense the sender, the guy on the outside, is commanding the object to do things. And the whole notion is not for doing commands, but for doing something else. Let me give you sort of a feeling for that. When I started thinking about this stuff for real, after I'd done a few failures, I came to realize that the only model that I knew of, either done by man or in nature, that really could handle complexity in any appreciable fashion was a biological one. The biological one, 90% of a cell's effort is going into its own protection. Only 10% of the cell's effort is going into contribute, or less, is going into contributing to what the organism is about. And the cells communicate both in the embryo and in the adult organism by sending messages around that they have very elaborate mechanisms to keep most messages out. Many of the diseases that we fall prey to, including AIDS, have to do with cells not being able to keep certain messages out. So that translated to me into, take the biological cell metaphor and try and translate it into machine terms. It's like you have lots of separate little computers running on a network able to send messages back and forth to each other. When you think of this as the ground base of object-oriented systems, then it's very difficult to think of this machine commanding this other machine. Because real computers have mechanisms for holding off commands. They don't have to listen to you if they don't want. And so the idea that each one of these objects is responsible for its own protection, and the strongest thing you should ever be able to do is to be able to beseech, please do this for me. But you shouldn't be able to say, do this for me, any more than you should be able to do the equivalent of an assignment statement. So one of the major things I worked on when I was designing the early Smalltalk was how could we get rid of the assignment statement as an imperative and replace it with something that was much more of a suggestion. And the amount of state that got changed, if any, was completely up to the discretion of the underlying object. To me, any language that doesn't implement that fully is not an object-oriented language, because what you have is something much more like abstract data types, where you have a bad old idea and you're trying to put béarnaise sauce on it in the hopes that it will be better. But béarnaise sauce on a hot dog doesn't help. So the basic two implications here is that you have an outside and an inside. The outside is completely behavioral. Messages can't be commands, and assignment has to be replaced by advise. If you have those two things, then you have object-oriented. Whether you have inheritance or not is not nearly as critical. Not nearly as critical, because in a good object-oriented language you can actually build it, and you may very well want to in some form of delegation mechanism. So these mysteries started becoming clear when I worked on this machine. This is the old Flex machine that Ed Cheadle and I did 20 years ago. 67 to 69. This is what it looked like on its own display. And it was influenced very much by Sketchpad, by Engelbart's first hypertext system, by Simula. It had a programming language I designed called Flex. It had a user interface that was so well designed, most people reacted to it the way you would if you opened up the lid of a garbage can and saw something moist and fuzzy down at the bottom. Or pretty much the way people react to APL today. I'm really proud of that user interface. Of all the things I've designed, it produced probably the most startling reaction. But did have a few ideas on it. It had a really good windowing system, one of the first. And it had multiple windows. It was a calligraphic display, so the windows didn't overlap back then. But a lot of the things that we're familiar with now in modern user interface were developed on this machine, although kind of ass backwards most of the time. So after wondering about what we should do, I realized that McLuhan made this great statement that I read one day. He said, "I don't know who discovered water, but it wasn't a fish." And I realized that as a graduate student, I was the world's worst user interface designer, because the whole thing about being a graduate student is to learn a really stupid system with 500 obscure commands just to prove that you can. When you turn a person like that loose on a user interface, you wind up with something like MS-DOS. So for a while I was thinking, well, I need some other context. There must be some other context. And I looked at some of the language work with chimpanzees. It was rather hard to get hold of chimpanzees. The Xerox corporate executives would never stay around long enough. So finally, for various reasons, decided to work with children who are also an alien species. But Palo Alto had bred hundreds of them just for our experiments. And once we started thinking about children as the end users, lots of things changed, because children had to have something so portable they could carry other things too. In other words, 0.5 herniations per block is not portability. So about 20 years ago, I came up with this idea, which is called we called the Dynabook back then. And it, my friend Dave Liddell, who is here today, when he was at the University of Illinois and worked for Owens Corning, worked on the very first flat panel display, which I saw a 1-inch square version of back in 1968, and realized it was only going to be a number of years before we could put all of the silicon that was in the flex machine on the back of the display, and that this would be one of the inescapable form factors of the computers of the future. So once starting to think about that and thinking about the children as the end users, it meant that things had to be much, much simpler than we'd ever done before. And one of the hints I got was from a great system done at RAND Corporation. Now, RAND probably has contributed more to user interface design than almost any other single place. Nobody knows that. Probably nobody in this room, or maybe only one or two people in this room, remember a language called JOS. JOS was designed in the very early 60s on a machine called the Joniac. And JOS was probably the best teletype or typewriter-oriented programming system ever done. It was the one that invented the interaction scheme that we now know of in APL, of having direct and indirect commands. That came from JOS. BASIC adopted it many years later, and so forth. And JOS had the misfortune of being implemented on the wrong machine, or else we would have been able to start much further along than a language like BASIC. So this language had been developed for non-expert users who are mostly economists who had to do a fair amount of computation. And these users loved JOS. In fact, I got a chance to use it in the 60s as well, and it was one of the few systems that you've ever worked on in which there was a pleasant little tingle when you knew you were going to get a chance to work on it for a few hours in the afternoon. How many systems can you say that about? You know, it was just there was nothing left to chance. Everything was done beautifully, aesthetically, and so forth. And the only complaint these economists had was they said, hey, none of us can type. We love this system, but we can't type. Can't you do something for us? So the RAND people actually went through their waste paper baskets to see what they did right. And I guess not too many divorces were caused by that. These guys used to write on legal pads and so forth, and they made diagrams. And so the RAND people in 1964 invented the first tablet. It was called the RAND tablet. I remember when we got one at Utah a few years later, 1967, one of those RAND tablets, 1,000 by 1,000 stylus pointing device, first good one ever done. 1967, that single device cost $18,000. And you had to hook it to a machine that was worth $500,000 to $1 million to make any use of it. A year after 1965, a guy by the name of Gabe Groner did the first really good gesture recognizer. And a few years later, they put this all together into a system called Grail for graphical input language. So let's run the second cut on tape 1. Here's what this looked like 20 years ago.
This list takes us back to where we may start to edit the flow diagram.
So no keyboard.
First, we erase a flow arrow, then move the connector out of the way so that we may draw a box in its place.
So it recognizes he wants a box and just makes one.
The
Now it's
printing in the
recognizing
box
his
is being
handwriting.
used as commentary only in this case. The box is too large, so we may change the size.
That's where modern-day window control came from, literally.
Then draw a flow from the connector to the box. Attach a decision element to the box and draw a flow from it to scan. We then erase the flow arrows attached to the process post new area and move the box to a new position. This allows us to draw a new box. Then chop off its corner and label it subscan with a residual error.
Now notice it misses the N here. He sees it, he hesitates, but it's modeless. So he just continues what he was doing, makes the change.
Correct the label. Add a decision on subscan so that control may flow to the 0. Complete the diagram from scan to post.
Okay, so I had a chance to use it for half an hour in 1960. It really changed user interaction. You're sinking your hands right of the display, touching the structures underneath. So it wasn't just personal, it wasn't just going from the mainframe to the desktop. This was intimate because you were right there. There were fewer barriers. Notice that the command scheme is not even menu-driven here. The commands are actually analogs to the results you want to have. So it's not just iconic, it's analogical. Very powerful set of ideas. Again, done on a machine almost the size of this room, but slightly less powerful than a 512K Mac. So this is a technology that actually got buried. We did many versions of this kind of stuff at Park. I used to show this movie every couple of months to my group so we wouldn't forget what it was that we were trying to do. And we're ready now in the next few years to see a rise of gesture recognition because the micros are now powerful enough to do this and still have some cycles left over for doing work for the user. And you may not know it or not, but actually one of the best groups in the country in doing handwriting recognition is at IBM. Big surprise, but you actually have one of the better technologies here. And so if you're interested in this, I suggest you look in the IBM phone dictionary for the group that is doing it. Now, John Scully was once worrying how many scientists there were at IBM. And I said, yeah, John, there are many more scientists at IBM than there are employees at Apple, but don't worry, IBM doesn't listen to them. It's just like at Xerox, you want them to let you alone when you're working, but then you want them to come around when you've got something. It's hard to get both to happen. So I want to intertwine some stuff in here because although this isn't really a historical thing, to me it's very important that the stuff that gave rise to what this symposium is all about was not at all disconnected from the fact that there are going to be users working on a system. And so the whole thing that brought forth real object-oriented programming and Smalltalk and the user interface that went along with it was that we had these children, and we wanted these children to not just be able to have access to things, but we wanted the children to be able to build things. So what we said was, if this were print literacy, we don't want to teach the kids just to read. Print literacy isn't just reading, it's also writing. We want the kids to somehow be able to write, and the equivalent of writing on the computer is not necessarily programming in the COBOL sense, but it certainly is building structures of your own. And so very early we got into this whole area of wondering, well, how does the mind work, if at all? And the first thing we discovered that whatever common sense notions we had about the mind working, they certainly weren't at all in accord with what had been discovered in the last couple of decades. For instance, common sense idea that's been in history for thousands of years is that because we think of ourselves as an individual, we think there's a single I-ness. And even in the work of Piaget, we see him thinking of the progression of an infant mind to an adult mind as something like the transformation of a caterpillar into a butterfly, that you go from something less form to something more form, but it's all made out of the same stuff, whereas the truth seems to be quite different and quite startling, that our mind is really made up of a kind of a patchwork quilt, modules or objects, if you will, and these objects communicate imperfectly because they came about at different biological times for different evolutionary reasons. And to give you an idea of the modularity of the mind, let's take a look at this. And let's see who in the audience can spot what's wrong with this picture. Besides the fact you've all seen upside down faces before. Who can see? Smile is what? Upside down, and what else? Teeth are, and what else? The eyes. Okay. So now if we were in school and I were a teacher, I would say to you, this is the way things are taught in school by language. I would say that what we've done here is we've taken a picture of a young girl, extracted the eyes and mouth, turned them upside down, put them back in with an airbrush, and then turned the entire picture upside down. Okay? So having said that, you should be perfectly prepared for what it looks like right side up. Now, I'm going to turn this back because I've discovered nobody will listen to me when it's on the other way. So that's interesting, that I gave you exactly the same amount of information 2 times, one through language and one visually, and you had a completely different reaction to the exact same information. That's the kind of thing that perceptual cognitive psychologists really love, because it means that different information going into different channels is going to different parts of the brain, and you're having different reactions. Therefore, there are modules. In this particular one, the module that's causing this effect, the 2 modules are actually known physiologically. They're located on the under right-hand side of the brain where you do face recognition, and about 1 inch apart from each other. One of them is an expert in recognizing face-like things. It's the thing that allows you to see faces in the clouds when children get scared at twilight with menacing shadows and so forth. That module is going off, saying, I see a face-like thing. And right now it's reporting, I see an upside-down face-like thing. And about 1 inch away is another module that's only interested in eyes and mouth. It doesn't care where they are. And it's reporting that's a good-looking mouth and those are okay eyes. And so the 2 descriptions basically have very little interaction. They're quite independent reportings from two different modules. Now, when I go to this version, the face guy is saying that's a right side up face-like thing, and the eyes and mouth guy is saying something is very wrong here. Now, you can imagine why nature might want you to be startled. See a face like this up close, it might mean you're going to die in the next 10 seconds. And in fact, this is not something that you learn. It's actually built into our nervous systems from birth, into most mammals, in fact. So if you try this experiment out on a dog, I suggest you pick a small one. So the important idea here is that there are modules. Just what the modules are is still open to debate. Some of the modules are even metaphoric. Not all of them are physiologically cited because of the way the nervous system is organized. We can have modules that are distributed all over the brain. So ideas like left brain and right brain are a particularly weak way of trying to characterize it. But the most important thing is once you realize that there's more than one module and that the modules have different ways of thinking about things and are somewhat recalcitrant and unable to talk with each other, then you have the basis for a much stronger user interface design or curriculum. Now, the ideas that led to this user interface that Norm was talking about, that was developed at the same time as Smalltalk, came from a Harvard psychologist by the name of Jerome Bruner. And Bruner had redone a number of the experiments of Piaget, but with some twists. So for instance, Bruner took a child who was in this middle Piaget stage, the image stage, and this is where you take a squat glass of water and you pour it into a tall, thin glass, and the child says, yep, there's more water in the tall, thin glass. And what Bruner thought to do is to then occlude the tall, thin glass with a piece of cardboard and ask the kid again. And the kid said, oh, wait a minute, there must be the same amount of water because where would it go? And Bruner would take it away and the kids would say, no, look, there's more, there's more. Bruner would cover it up and the kids say, well, hey, wait a minute. So if you have any 6-year-olds you'd like to torment, and Bruner did many experiments in the 50s and early 60s, and the conclusion was that what we didn't have was a progression of stages of the caterpillar going to the butterfly, but instead what we had were multiple mentalities and a change in dominance, because Bruner could show the existence of the previous and mentalities to come by various tricks. And Bruner said, well, there are lots of different mentalities, and he picked 3 that he could show the existence of and concentrated his curriculum ideas on those. And those 3 were a kinesthetic mentality, identical with Piaget's first stage, where a hole is to dig it, an object is to grab it. The iconic mentality that we just talked about, and then around 11 or 12, a symbolic mentality where facts and logic are used, or at least in Swiss-French children around 11 and 12. American children have a very difficult time ever getting to the facts and logic stage because we have an enormous iconic barrier between them, which is called television. Now, the existence of these 3 mentalities, they each have striking characteristics. And in a nutshell, as I can only go into here, the kinesthetic mentality is the one that places you in space. It's not your visual mentality as you might think, because you can blind a person can be blinded and still have a perfect sense of where they are in space. But if you remove for instance, a person's limb from their body map, as sometimes happens in an accident, then they may have a perfectly healthy leg attached to them, but they cannot feel that it is there. They relate waking up in the middle of the night with somebody else's leg in bed with them. And in fact, they have a very hard time looking at their leg to see that it's actually attached to their body. There's kind of a blur there because, of course, we see not what our eye sees, but what our brain knows. We see a simulation that is pieced together, and our brain has had its knowledge removed that this limb is part of us, and it's very hard to actually see what it what it actually is. So the kinesthetic sense is the one that places us in space. It is the one that, when removed, is the most alienating. The contact one is the deepest one, the oldest evolutionary one, the tactile sense. The image one has two main characteristics that are worth noting. One is the ability to remember images after only a brief exposure is astounding. Haber, who was a psychologist in the 60s, did several experiments where he showed 2,500 photographs spaced 10 seconds apart. It's just a bunch of slide trays for hours until they'd seen 2,500 images, all sorts of random pictures. And he discovered after 30 days that all of the experimental subjects had a better than 90% recall of those random slides and could even identify occluded parts on slides and so forth. This is an experiment you can do yourself. Get a friend to manipulate a cable TV movie channel and have them dial into a movie you haven't seen for 18 years and see how many frames of the movie you have to see before you can identify it. Most people can do it in under 90 frames. 3 seconds of exposure is quite enough for them to say, yep, I've seen this movie before and I know here's what's going to happen next. Now think about what that means. 18 years ago you saw this movie. You're being put into the center of it without any preparation and stuff, and for some reason your visual system can organize all of those pixels, or what the pixels have turned into, to be able to perform that recognition. So it's striking. Recognition is also fast. So you put 100 pictures on a bulletin board, you can find a specified picture 4 times as fast as you can find the word in a list of 100 words. So it's much more efficient. And this recognition and comparison and stuff is done by a completely different part of the brain. Visual system is also the mentality that is least blocked because it's very modus operandi is to flit around and take in different parts, not to become fixated in one thing in the visual scene. So it's, there are many things you can do that in which an access to visual scene augments the short-term memory and boosts creativity. Then finally, the facts and logic system, which is what we concentrate on in school, unfortunately, it's strong in many ways because of its abstractions, but it's actually the weakest mechanism that we have. It only works when there's a strong context. So when we were thinking about these ideas, we had this basis from Brunner, and it took us 3 or 4 years of experimentation to come up with this motto that what we really should do, this is something that's been misunderstood about this user interface because it's always talked of as the graphical user interface, but in fact it was an attempt to combine 3 mentalities into some kind of synergy. So the doing with images makes symbols says there's some kind of progression, which Brunner identified as well, that if you can learn where you are, learn things tactily, that gives you a much better set of hooks for your image system to put things on, and then at the very end you have something to abstract that you want to, for instance, if you want to learn physics, the best way to learn it is body physics and visual physics before you start looking at calculus. Then you have intuition. And Brunner claimed that, and I believe him, that what we call intuition is simply these mentalities that don't talk, sort of vaguely whispering to us somewhat variant thoughts than the one we call I actually does. So if you take those ideas, the way we picked, and we didn't even like the mouse, but as I said, tablets were expensive, and so we took Engelbart's mouse and made a better one and let that be our pointing device. If you believe what I'm saying about the user interface, then it would suggest, number 1, that we should have better pointing devices, and number 2, that the pointing devices should start to give us some force feedback back into our hand, because then the kinesthetic contact would be much greater. And the windows and icons are for the purposes I've just mentioned, and we came up with Smalltalk to be the underlying symbolic framework for all of this stuff. This is why on the Macintosh and the Macintosh imitators, that the pointing scheme is not functional. You don't give the command first and then be stuck in a mode and go out and then try and pick parameters for it. What you do is you do it exactly the same order that you do object-oriented programming, and that is you designate the objects of interest first, and then you send the messages. So translated to user interface, it says selection first, messages later, and that gives you an approach to doing modeless interaction. And here's an interesting idea that we implemented at Park, but in fact has never made its, I just cannot believe that this idea has never made its way out into the world, because it is a direct implication of object-oriented design. The implication of object-oriented design is not cutting and pasting. That is absolutely at odds with an object-oriented user interface. This is the implication of object-oriented design. This is a document that has a variety of different paragraph types in it. One of them holds text, another one holds pictures, and these are, as Norm was pointing out, these are the applications themselves. So you don't go out to another app, you don't go out in this system, you didn't go out to a painting system to make this picture. The painting was actually developed right in the context of the document, because you just started a new paragraph type there. And what you see here, this is a page from the Lord of the Rings, and the cursor has just gone into this picture, and what has happened is it sprouted a menu because it thinks you might want to edit it further. So as you go into each paragraph type, it activates the sub-activation, the sub-application, if you will, so that all of the things that you're working on are in the context of your result. It's the thing we call results mode interaction, which I think is one of the most important aspects of WYSIWYG that hasn't really made it into the outside world. Always keep the user working in the context of their results. And that means they shouldn't go out to other applications to get values and bring them back. They should be able to develop the values that they want from within the final thing that they're working on. Now, this next, in order to talk about this next part of the talk, a little more context. If we think about the two ways that humans have extended themselves over the last several 100,000 years, one of them is by making amplifying tools. Physical tools like the lever and the wheel, figurative tools like mathematics, like language itself, and so forth. All of these I think of as being extensions of manipulation. Even mathematics, which we think is something fairly abstract, is actually a way of taking the hopelessly abstract, making it into concrete things that we can then move around. So all of these things I think of as being manipulation. The M word is manipulation. And the other, and of course, the Macintosh user interface is that style. It's basically make everything into an object. And as Norm mentioned, if you take things that are verbs in English and make them into objects, you have a much better time of it, because of course the universe doesn't seem to have any verbs. Right? English was invented to talk about horses and cows and plowed fields and so forth. And it didn't anticipate modern physics, which, as far as we can tell, there are no abstract verbs out in the universe. Instead, what we have are things that are much more like objects in process. So when I hear a sentence like the clock runs down or the boy runs down, the only way I can come up for any meaning of what runs down actually is all about is by thinking of it as an attribute of the subject of the sentence. Okay? And there's enough metaphorical similarity between the two items so that we can use the same word. But I always think of what we think of as a verb as really an attribute of some subject. Otherwise, the sentence wouldn't make any real sense. And that is in accord with modern physics. So the other way we've extended ourselves over the years, what I call goal cloning. Goal cloning means that we simply are able and willing to go out and convince other people to take on our own goal structures. That's how we get most things done. That's what's going on here. We have a group that has, for the moment, has fewer goals than the sum of its parts. And companies are that way, countries, cultures, and so forth. Sometimes the methods are crude, as in the way the Egyptians got the slaves to build the pyramids. Sometimes they're slicker, like in the modern television advertisements. Mumford called this building a mega machine. He pointed out that over most of recorded history, most machines built by human beings had human beings as parts. And the M word for this to me is management. That you manage that kind of process and we manipulate objects. And we're going to see a transformation from actions having to do with objects into agents, which we are going to manage. Now let me give you two examples. The first is sort of an example of what you can do with a tool and what a tool really means. So let's show I want to show tape number 2. So this is a 22-month-old young girl who never lived in a world not densely populated by Macintoshes. Her mother's my accountant, and both her mother and father work at home, and each of her mother and father has a Mac. And of course, to her, this isn't technology. Technology, all that stuff that wasn't around when you were born. We did think pencil and paper technology, wristwatches, radios, any of that stuff. So she never seen anything. I found out she was interested in computers. I gave her an Apple II, but she rejected. And although I don't believe in user surveys much, I did one with her, and I discovered she vastly preferred personal computers and installed hard disks. Even though we developed this user interface for children, I've never seen it used by a child anywhere near the young, so I was quite intrigued to see how she did. Here she is doing visible menu command, Mac Paint. And of course, she didn't have to get the mouse. And I thought, well, okay, I'll go along. This is interesting, but I wasn't really impressed until I saw what happened next. She wants a fresh sheet of paper, so she used the close box in the window and saves her old drawing with the pop-up, then goes to the pull-down. That's breaking. Okay, you can stop that. The implications here that's kind of interesting is do the user interface at all in accord with what's actually going on inside of people's head, then you get something that can actually extend all the way down into childhood and be to them as fundamental as the marking instruments that we grew up with. And I think this is very important because I believe that the children that can form themselves by being around this media, as media, are going to be thinking and doing things very differently than the way we do. This is another example of, in the long line of how we act smarter by changing our representations. We go from Roman numerals to Arabic, we go from Ptolemaic to Copernican. Every time we change the representation system, our weak systems of logic are made that much stronger. And I think of user interfaces, main aim is not to present, but to represent. And it's figuring out what those representation schemes are going to mean in terms of the leverage they give the user that is the most important point. That point has been missed in most people who are doing user interfaces today, including a lot of the people at Apple, and certainly the Apple imitators, because they think that the whole job of the user interface is to present old-style applications with multiple windows and pull-downs and so forth. Nothing could be further from the truth. The most important aspect of the multiple windows stuff is not to have different applications up there, because as I pointed out, that's not the way you want to go after different parts of the things. The most important thing for having multiple windows is to be able to present different points of view on the same thing. Marvin Minsky says you don't understand something unless you understand it in more than one way. And almost no one who uses these user interfaces thinks to sit down, even though Apple showed them in the Finder that you want to have multiple views of different kinds of things, thinks of what the leverage means is to be able to look at the same kind of thing from multiple points of view and what it means pedagogically. Because once you've seen that, you realize that if I only know one point of view about something, I don't know it. In fact, I'm likely to be misled by it. So now let's take a look at the other way that's just starting to come in and think of why it's going to. Why are we going to have management of semi-intelligent computer processes now? I think it's because we're starting to be networked up, and there are a whole bunch of things that networks give you as opportunities that we simply don't have the time and the scope to deal with. I'll give you an example. when I was a kid, I used to get questions answered by going into a library, and once I was visiting some friends in Washington, D.C., and I had a question, so I demanded to be taken to the library. I'd heard there was a library in the town. And we got to the Library of Congress, and I discovered that the card catalog, which they didn't even allow you to go in, was much larger than my hometown library. And instead of having you do the browsing, they had people who would meet you at the door. Their job was to absorb what your goals were and then apply their expertise of the facilities to that. So they became your agent, and they even would energize other agents. So my problem turned out to be fairly interesting for one brought in by a 9-year-old, and so we had 5 or 6 adults scurrying around trying to find the answer to it, and it left a lasting impression. And this notion of agents is as old as computer interfaces itself. It goes back to McCarthy's original advice taker paper. It basically says that when you have an information utility, there's going to be an embarrassment of riches organized in a way so that no human will have the time to go after the stuff. No human will be able to remember all the things they might be interested in, and so something else has to go and do it. Now, the problem with agents in the user interface sense is that AI has not progressed much since 1970. It is extremely difficult to build an agent. I have built several over the last 8 years or so, just to see what they would be like, and they're excruciating to build. One of them was a system called Newspeak at MIT that stays up all night trying to find for you the newspaper you'd most like to read at breakfast. So what it does is to log into a dozen or so information sources: New York Times, Associated Press, Nexus, Reuters, looking for articles it thinks you might be interested in. It reads the articles to the best of its ability. If it sees a famous name like Mitterrand, it has a video disc of 45,000 pictures of famous people. It's like a newspaper morgue. It picks a picture of Mitterrand. There's a map disc with 37,000 maps, and so forth. Uses an expert system to format the page, and you wind up the next morning with something that is very much like USA Today. and often with about the same amount of content. But there are some differences, because the headline might say more fighting in Afghanistan, or it might just as well say your 3 o'clock meeting is canceled today, because one of the 12 news sources it logs into is your own electronic mail. It reads it while you sleep. If it spots anything that looks important, it puts that in the newspaper the next morning. A sidebar might say your children slept well last night. Because remember, what we call news is entirely dependent on the communications system that we have. In the late 1700s, the news was all about depth. The Federalist Papers were published in the newspapers of New York City. Something that would be unthinkable today, actual essays. But people had time to read them. When the telegraph got invented, all that went away because they couldn't possibly have you reading anything long that had to be thought about and understood, because you'd still be working on it when the next news came along. So currency, and as McLuhan predicted, as soon as you start hooking up news to electronic media, you start getting fragmentation. So that's the idea of an agent. That newspaper is something that people would like to have, but nobody is going to sit up doing it, even with the best SQL-type database and so forth, because it's very hard to even remember all the things that you're interested in. So the agents also are going to be somewhat anthropomorphic. This is a real problem because they aren't going to be very smart when we start off. So we have to, in the user interface design, somehow subliminally project exactly how smart they are and still make the user, we want something like a puppy dog that goes out and gets your newspaper most of the time and only occasionally makes a mess on the floor. So let's take a look at, this is a video we made for John Scully, and we start off at the 1988 Winter Olympics in HyperCard, a HyperCard stack that ABC Television used to keep track of things, and then we project 4 years into the future and see what things might look like in 1992 with a user interface that is still mostly manipulative but has a little bit of the management aspect to it. Let's roll tape number 3, please.
It begins as you're running on top. As someone's thus involves map of Calgary. If you click on any Olympic site, you see a list of the events scheduled for that site. You can get more information about any event by clicking on the name. Let's say ski jumping. Background may. You can branch back to the events or the main map and then continue exploring. Here at the University of Calgary, I see the figure skating events are running. Now that's a sport my family's interested in, so I'd like to learn more about it. The previous Winter Olympics took place at Sarajevo in 1984, when Macintosh was barely a month old. Imagine what Macintosh together with HyperCard will allow us to do in another 4 years by the time of the next Olympics. We will require powerful techniques to help us find and manipulate volumes of images, text, music, video, and applications. We might by that time see the beginnings of intelligent agents, or perhaps by then they'll be only semi-intelligent. Phil?
Today is March 3rd, 1992. You have several data service articles ready, and you have mail.
This is my agent. I call him Phil. Phil, open the 1992 Olympic stack. The 1992 Winter Games are being held in Albertville, France. Let's get a closer look at the town. Let's look at ski jumping again. We can play the video. We could learn more about this sport or go back to the map. Let's look at figure skating. I'd like to see who's on the USA team. And I'd like to see Debbie Thomas. I'm looking for a spin. Like that. Let's go back. Alan Kay was explaining why skaters go faster as they tuck their arms in. He showed me a simulation to illustrate the underlying principles. Let me call that up. Phil, add the physics draw toolbox.
Which toolbox?
Physics draw. Let's see, I'll need a counter. We can make the window translucent. Let's step through the spin and count the frames. Okay, that's one complete rotation. Now I'll draw a model representing a skater with her arms extended. Select the center axis and rotate.
How fast to rotate?
This speed. And here's an overhead view of the figure. Let's hold on to that. Earlier, Alan and I created a similar model where the skater has tucked her arms in and appears to be spinning faster. Phil, display skater model 1. Let's compare these two models. The small one, the one with the shorter radius, seems to run faster. But let's check that. I'll set them both to run for 0.3 of a second. The small one turns farther around the circle, but let's see how much distance is actually covered. I'll straighten out the curved paths to measure them. Both paths are the same length. Even though spin increases, the distance traveled is the same.
The luge event is about to begin. Show it live or record it?
No, I'm not interested in luge.
I don't understand.
I like skating.
I don't understand.
Don't show luge. Don't record it.
I understand.
I'd like to save this simulation. Phil, start a link. Phil, show the stack map. Too far. Okay. Show recent. Link to this background. Now anytime I'm on a skating card, I can link to my physics simulation. By the time the Winter Olympics come to Aberystwyth in 1992, CD media will be well established. Each of us will be able to choose our own path through worlds of entertainment and information. And tools like those that we've been seeing will allow us to integrate the full range of sound, video, and text information.
This demo ends here, John. Should I show the pre-recorded speech, or will you give it live?
So, two main things to think about here are that although we are, of course, going to go to hypermedia and it's going to be object-oriented, it's really not going to be complete until the user is able to do active thought experiments. Most hypermedia up till now assumes that the user is going to navigate around stuff that may be active, but the user isn't going to be able to do a lot of creation themselves. And this is a critical thing to realize. And that the agents of the future are going to be helpful mainly for their ability to work away from us, not from the amount of comprehensiveness that they have. The best object we have for exploring this new area is the one between our ears, providing it's active. Thank you. Thank you. So some questions? Yes. Yes. Well, you can do that, but just consider the problem of a system file that some people have access to and other people don't have access to. Right? There's a perfect example of when what you would really like to have is when somebody sends a message, not a command, but a message to that system file, you'd like to have some way, number one, of checking the access privileges before you do anything. And number two, you'd like to be able to do that checking quickly. Okay? But even being able to do the first would be good, whereas in the current things that are called object-oriented languages, you are already committed. You've already formed an activation record because it's a procedure call. You're already inside the method, and thus each method that is sensitive has to have the responsibility to the access. You can put that in. You can put a call to a procedure, and you have to remember the next time you do a method that has this problem. That isn't all. I mean, language also allow you to learn things that allow you access in various ways. Smalltalk allows you to turn a thing called a block. And that block is a particular kind of object that, it's a block context actually, that by virtue of what it is, it has access to some of the internal variables of the object. And so it's, you can create Trojan horses and so forth. But basically what happened is when they were implementing the newer versions of Smalltalk, some of the older people who worked on it didn't work on the newer ones, number one. And number two, most of the newer people had never done any operating system type stuff. And so the operating system type stuff that was in the original one didn't get put in as the later Smalltalk went back to be looking a lot more like Simula than the original one did. The original one, when you sent a message, you weren't calling a procedure at all. All you were doing is knocking on it and saying, hey, you know, it's the equivalent of the postman leaving a thing that says there's a message waiting for you down at the post office if you would care to get it. And there was that arms-off relationship that Smalltalk 72 had that allowed you to implement all the operating system protection ideas that are important. And I think that the ability to implement large systems in object-oriented languages, as well as being able to implement them conveniently, is going to have a lot to do about how much protection integrity there actually is. It's easy to do. You just have to know that it's important and put it in the system. Yes? Right. Yeah, well, I think, again, I had there's a little technical part of the talk that I left out, but I think that one of the things that's going to happen is that the way we're thinking about objects now, just even as people are struggling to use them, one of when you look at object-based systems today, they're mainly modular in terms of state. Right? The state is sealed off, and sometimes it's not even state, because you can have procedural interpretations for things. And the thing that's not modular in object-oriented systems is control. In fact, it sometimes gets worse, because you can have what's called a buck-passing theory of control, where you're constantly passing control all over the place, and eventually it gets to somebody who can handle it, and they handle it. And it's both through inheritance and also through containment that happens. When you start looking at a system that's been implemented that way, you start realizing, whoa, all of a sudden you have to start understanding things again. And the whole idea of object-oriented programming is to be able to program things without having to understand how everything works. It's like Prolog. It's like magic for about the first 3 hours, and then all of a sudden you have to understand 10 times more than you ever did. So it's kind of a cruel trick. And if you look into biological systems, again, the first Smalltalk was designed more this way. It was less procedural in many ways, and it was hoping to use a control structure invented by Dave Fisher, who did a great thesis at Carnegie in 1970 called the Control Definition Language. And that was one of the inputs to the design of Smalltalk. And there he was very interested in what you might call agoric computing. And the current stuff I've been fooling around with are systems that don't send messages but only receive. In other words, one of the ways of getting around the control problem is to, if you're a module, what you do is let the system know what you're interested in, and it's up to the system to somehow get that information to you. You don't care how. What you don't want to have is a system which every time a new object goes into it, some other object has to know it should send it a message too, right? Because then you're right back to something analogous to the data structure problem of having random procedures understand the formats of data structures. And here we're talking about having objects having to understand essentially control formats. So I've been working on a design of a system that only receives, but it receives by indicating things it's interested in, and then the system constructs a structure that will guarantee to deliver that information to it in a timely fashion. And again, I think if you just get away from software systems and think about networks again, it will tell you a lot about what to do with objects. Because you really, you can't take objects seriously unless you think of a transmission line between them. It's too easy to just think of sending a procedure call to them. You don't have any of the interesting things that happen with concurrency and synchronization and protection and all of those things that are really going to be a major part of just standard programs that we're doing in the world. So I think if you just think of it as being a whole bunch of network computers trying to cooperate and realizing what the problem's there and how you want to write the code, then I think it tells you what to do with objects. That was the way the original Smalltalk was designed anyway. Yes? Right. Good question. I don't actually have any of those things in mind, but when Smalltalk 72 was done 16 years ago, the idea back then was what capabilities could do. Capabilities are a short way of dealing with access rights. Okay, and the access rights there are at the instance level in capability systems. And I wouldn't think that trying to protect at the class level is, see, it's easy to protect the class if you can protect at the instance, right? Because the class is an instance of class. So it's trivial to do. So you want to protect at the instance level itself. And protecting at the instance level in capability systems is tantamount to protecting each message individually, because that's what a capability map actually does for you. So it's a very nice way of doing it, yeah. Sure. No, I don't see any. If he can deliver it for that price, I think he'll sell a few. But as far as I can see, there's no. In fact, the interesting thing is the user interface. A lot of the things in the user interface are more like Smalltalk than the Mac. He has hierarchical browsers in it, and the proportional scroll bars and other kinds of things that Smalltalk had. Although he has a very strange window resizing method, apparently. I haven't actually used the machine yet, but somebody told me you can only resize one dimension of the window at a time. And he would have known that Apple didn't own that if he'd seen the Grail movie, because that was done 20 years ago. Yeah.
Can you talk about techniques you need to do these activations?
Well, again, in the longer talk, when I started thinking about it, I realized I not only didn't have any good ideas about AI, that I'd never had a good idea in AI, and I figured that was either because I was completely stupid, or else I was thinking about it in a way that wasn't terribly fruitful, or the stuff that people have been doing in AI didn't have any good extrapolation into what would be powerful. I still don't know which of those three is the case, but I have a couple of degrees in biology, so I started thinking about it from a biological standpoint. And the first thing that I realized was that trying to essentially do a Beethoven, which has been one of the main aims of AI, is to do some superhuman intelligence right off the bat to impress the Pentagon sponsors, is a real loser, because we can't even do a decent ant. And so I got interested in thinking, well, what would it be like if you forget about Beethoven for a while? What would it be like to just try and if you think of AI as an architectural problem, which I do, just as I think of life as an architecture, right? The material moves through us. We recycle the atoms in our bodies every 7 years or so, but the pattern remains. It's kind of a weird feeling to think of matter passing through this force field or so that organizes it. And the same thing is likely to be true for intelligence. That it's an architecture, and when you're doing architecture, you have to start building things and seeing which cathedrals fall down. And you're really in bad shape in architecture if you build doghouses, because you can build a doghouse out of almost anything, and it won't fall down, and it doesn't scale. The big problem with our whole field is good ideas don't often scale. And we always get screwed when somebody has a good idea that works in the small, and then they try and scale it up by a factor of 1,000, and all of a sudden it doesn't work anymore. So to me, it seemed like an interesting thing to do would be to try and build some biologically relevant models of animal intelligence and pick at a bunch of different levels so that you wouldn't get into the scaling bug, so that you actually thought you were developing something that might give you a few hints as to what a good architecture for intelligence is. And I joined up forces with Marvin Minsky at MIT, set up a project called the Vivarium, which involves children, because again, it's hard to design for adults. It gets boring after a while. So the project for children wound up being saying, what would it be like for children to actually build these animals? So what would it be like for a child to sit down and build up both a physical animal and a mental animal that you could put into a big environment? If we have one more second, I can show you a little clip of some of the work that we've been doing. This will be tape 6. And what it is before you show it, what it is some real stuff and some fake stuff. The real stuff is all of the 3D graphics that are in it, which we did in real time on an Evans and Sutherland flight simulator. This is a machine that has something like 3.5 gigaflops of computation. It's about 6 to 8 Cray XMP48s worth of stuff. So it can actually generate on a database that is subplanetary in size. Because you have to fly over hundreds of miles of it at Mach 3. And it's able to perfect anti-rastering, perfect texture mapping on the thing, and it has it has the ability to have as many as 32 independent cameras at once. So you can look into the same database from multiple points of view. So all of the stuff that you see in this user interface at that level is real, and then what we did is a little mock-up to see what the user interface, some of the elements of the user interface might be for children. We're using elementary school children, so they're both visual and very tactile. So we got very interested in what would a tactile kind of user interface be, and particularly one without any menus in it. So I think you'll be able to tell the difference between the two. So let's roll that tape number 6. So here, just turn out the lights. So here we have actually 4 desktops in operation under projects, and we go into the vivarium one. And here's the flight simulator. We have 2 different points of view, 2 camera controls, as you see there. So this is 60 frames a second, real-time computer. We wanted to do it all in real time to keep honest about it. And one nice thing about real-time graphics is if you want 3 minutes of real-time graphics, it only takes 3 minutes to generate. So here's the little kid's notebook showing a rockfish. We see the real crab over there and the simulated crab and the crab model that the kid's working on. Here's the sea snail. That weird color it has is actually the color. That's how we do scrolling. And here's an avoidance reaction. This is what a real one looks like. Really an amazing color. And down in the sail simulation here, it's just chugging along on its basic movement cycle. These snails, these particular ones have only about 2,000 neurons. So here we open it up a little bit. Kids love that. Various brain models. There's 3 or 4 different points of view. Here's the one that they would use to program it with all the sensors. And now if we put them all to work, we get to see what the whole environment actually looks like here. this is about 2 years into a 6-year project where we basically built all this stuff by on the flight simulator. The brains of the animals we built with a bunch of thesis projects at MIT that Marvin Minsky and I are supervising. The next phase of the thing is to do a system now that children can actually build the animals and put the brains in. So we're, the idea is about 2 years from now is to start testing that aspect of it. By the end of the 6 years is to exhibit sort of an animal building kit with brain models that ethologists would not turn up their noses at. Thank you very much.
We're going to take a break, and it'll be 10 minutes. Please return in 10 minutes. Thanks.